In this set of videos, we're going to learn a hidden Markov model, HMM. HMM has been widely used in many fields. I don't think I need to spend time to explain or introduce its potential applications. You can do a Google search and learn some interesting applications of HMM. In HMM, the data we observe are x's. So we'll sequentially observe x1, x2, all the way to xn. And the distribution of the x's is governed by a set of latent variable z1, z2 until zn. But we don't observe z's, we only observe x. And those latent variable z's are further modeled by a Markovian process. Both x and z can be either continuous or discrete. But by convention, usually HMM refers to the model where z takes discrete values, and when z takes continuous values, it's often referred to as a state space model. For simplicity, we're going to focus on the case where both x and z take discrete values. But all we're going to learn today can easily extend it to the case when they are taking continuous values. Well, this is a simple toy example you can find from our R page. And consider a dishonest casino which uses two dice. One of them is fair, another one is loaded. So here's a distribution for the fair die, and you can do, once you throw the die, you're going to see the 6 values and equally likely. But for the loaded die, and the chance of seeing 6 is very high, it's almost 50%. As an observer, you won't know which die is actually being using because the state is hidden. But you will be able to see the result. For example, we can generate some outcome from this dishonest casino toy example. And this is what the output look like. And here, let me draw this. So this is a time. And so this is capital T, and this is 1, 2. And what's drawn here are x sub t. So at every time t, the x sub t will be equal to one of the 6 values. So you're going to find out if xt is equal to 3, hypothetically, then we're going to draw a bar at the third line. And so at every time t, you're going to see one and only one of the 6 lines and get a vertical bar, because that's the value of xt. And once we see this data, of interest would be to estimate the hidden state z. Here, the hidden state take 2 different values, either a fair die or a loaded die. So we'll be interested going back to look at during which time which die is being used. For example, and this is actually from the algorithm, and our algorithm can tell, well, during this time range, seems the loaded die was used. I think red referred to loaded. And during this region, there's a high chance the loaded die is used, and similar here and in those regions. And the results seems reasonable because we do see a cluster of those, high chance of getting 6 during this time range. And once we have learned the underlying distribution of z and among z and also between z and x, we might be interested in predicting what will be the outcome for the next at the next time point. So for this hidden Markov model, we would be interested in learning the hidden states, but also we might be interested in doing prediction. To get a better understanding of HMM, let's think about how to generate HMM. First, we have to decide the number of hidden states, meaning what are the values z can take. And we use m sub z to denote the number of unique values z could take. It is a tuning parameter. It's almost the same as the number of cluster K in the mixture model. And how we're going to choose MZ, we can use AIC or BIC once we estimate the model parameter. And we also need to know how many values X take, but that's not a tuning parameter. Once we see the data X, we would know how many unique values X can take. So remember here, we assume both X and Z are discrete random variables. And then next, how we start generating the model. Well, we first need an initial distribution W, which is a probability vector of size m sub z times 1. So that will specify the initial distribution for the first hidden state, Z1. Once we specify W, then we can generate our Z1. And then based on Z1, we're going to follow the arrow and use a Markovian property to generate Z2 and then Z3 and go on. What do I mean by Markovian probability? I mean that the Z's is a Markovian process. So to specify the distribution, once we already generate Z1, to generate the next Z, we need a transition probability matrix. It's called A, which is MZ times MZ. For example, if MZ is equal to 2, let's consider the casino case. This one equal to 6. Then this will be a 2 by 2 matrix where the first row, the 2 number in the first row, should sum to 1. And it tells us once you at state 1, how you stay at state 1 and also move to state 2. Let's consider the casino example. So MZ equal to 2, we have 2 hidden states, and MX is equal to 6. So A will be a 2 by 2 matrix. It's called a transition probability matrix. And every row should be a probability vector summing to 1. So for example, if this is the first row is 0.8 and 0.2, it means that if you're already at state 1, then with chance 80%, you're going to stay at state 1, and with chance 20%, you're going to move to state 2. And for the second row, suppose it's 0.5, 0.5, meaning if your current state is state 2, your Z is equal to 2, then you're going to, with chance 50%, stay, or with chance 50%, you're going to move to state 1. So how we can use A, once we generate Z1, we can use this A to generate all the remaining Z's. For example, if Z1 is equal to 1, then we just look at the first row of this table to generate Z2. Now suppose Z2 is equal to 1 again, then we again look at the first row of A to generate Z3. And suppose Z3 is equal to 2, then we're going to look at the second row to generate Z4, and we keep doing this until we finish generate Zn. So using W and A, we can generate the latent sequence Z. Then we need to, given Z, we need to generate X. And in the dishonest casino, we know that there are 2 different distributions over the X. And we call that the emission probability matrix, and throughout I will use B. So it's always equal to MZ times MX. So in this case, would it be 2 times 6? So every row will be a probability distribution, and the probabilities sum to 1, meaning if the Z is equal to 1, then we're going to use the first row to generate the corresponding X. If Z is equal to 2, then we're going to use the second row to generate X. So the hidden Markov model in some things is like a clustering algorithm, and it's a mixture model. We try to cluster those X's into MZ different groups because the underlying distribution for X's will be different. There are M sub Z different distributions. However, because of the time, because of the index 1, 2 until n, those X's are not independent. There's a natural temporal relationship among those x's. So this is why we model the latent class, latent variable z, not as IID, draw from MZ different values, but there's a Markovian process. In this representation of HMM, I use arrows because they will help us to understand how the data are generated. But later on, I wanted to remove the arrow and only represent this model using undirected edges. The reason is that HMM belongs to a bigger class of statistical models known as graphical models. In particular, HMM is an undirected graphical model. And what is a graphical model? In graphical model, we try to use a graph to represent the conditional dependent structure of those variables. For example, in this case, we have two random variables, and whenever there is no edge between two variables, means they are conditionally independent. So for example, for x1, x2, there's no edge between them. That means conditioning on all the other random variables, and x1 and x2 are independent, which is intuitively true because x1, x2, their distributions are totally determined by their corresponding latent states, z1 and z2. So once we condition on z1 and z2, x1 and x2 should be independent. But when there is an edge between two random variables, means even with conditioning on all the other random variables, they are still dependent on each other. For example, z2 and z3, there is an edge, means even with conditioning on all the other z's and all the other x's, there is still some dependent structure among z2 and z3. You will see that this kind of a conditional independent structure or dependent structure will help us to factorize the joint distribution between x's and z's. Well, this is a recap of what we have discussed so far. For hidden Markov model, we have observed the data x. We also have latent states z. Let's assume, for this lecture, let's assume both z and x are discrete random variables taking m sub z and m sub x possible values respectively. And a hidden Markov model is parameterized by the following parameters. We have w, which is the distribution for the first hidden state z sub 1. We have the transition probability a that models the move generation from zt to zt plus 1. We also have the so-called emission probability distribution that models the distribution from the hidden state zt to xt. And all those five symbols, well, including those two, they are the five essential components of a discrete hidden Markov model. The main issue with hidden Markov model is the computation. Next, we're going to go through the technical details on the computation for the following four quantities related with HMM. The first one is the forward probability. It is the joint probability of observing a data sequence x1 through xt, and also at the tth time, the hidden state is equal to I. Here we assume the data x1 through xt are all given, so this probability is really a function depends on the time t and also I, which is the value of this latent state at the last time point. First, why this is difficult to compute? You're going to find out the probability involving hidden Markov model is very easy to compute if we conditioning on or if we could observe all the latent states. And when we leave out some of the latent states, then the computation is basically just a sum over all possible values of all the latent states. In this case, this probability is basically a summation of all the latent states of z1 and zt minus 1, which is, there's no way you can simplify that computation. And so the strategy you're going to learn is that we're going to recursively compute this, starting from t equal to 1 and all the way until t equal to n. So this is why we call it a forward probability. And why we would be interested in this quantity? For example, suppose you compute this alpha ti for alpha t1 all the way to alpha t mz. So for simplicity, let's just assume our mz is equal to 3. Okay, so we have alpha t1, alpha t2, and alpha t3. Those are 3 numbers. If you normalize them, meaning they divided by the 3 numbers by their summation, then you get the conditional probability of zt equal to I, conditioning on the data you observed all to time t. So this is an interesting quantity because it tells us the uncertainty of the latent state at time t given all the data till now. And another interesting use of this forward probability is to get the marginal likelihood of the data of a hidden Markov model given the parameter. So given the parameter, even the parameter is given, computing the joint likelihood of x is difficult. And you're going to find out it's basically equal to the sum of the alphas at the last time point when t is equal to n. The next related quantity is called backward probability. And it computes the probability, conditional probability of zt is equal to I. Given zt equal to I, what is the chance of seeing future outcomes from t plus 1 to n? This will be an interesting quantity because in inference, it will tell us at time t, suppose we know the hidden state at time t is I, what will be our prediction or our distribution on future data? Those forward and backward probabilities, for those computation, we assume we knew the hidden Markov model parameter. Of course, a much more interesting task is to estimate this parameter, and we're going to use MLE, meaning we're going to find out MLE of theta that maximize the marginal likelihood of this observed sequence X. It's going to be difficult, and we're going to use the EM algorithm. Once we have estimated the theta, and next thing we wanted to come with some inference about the latent states. Suppose we have already estimated our theta is theta hat. Then what can we see about the latent states conditioning on the data we observed?